Yeah, well, so thanks to the organizers for inviting me to give a talk here. It's the first conference I've been in person in about like 4 years because of the pandemic. Also, thanks to Yuval for agreeing to switch talks and do his talk 2 days early, since I wasn't able to really speak out loud on Tuesday when I was originally going to give a talk. Okay, I'm going to talk about something related to a project I've been working on that's related to NIP rings and also definable field topologies on NIP fields. So I've given a couple of talks on this recently on different aspects. One of them was about the sort of topological fields and that kind of thing. Another one was about the Henselianity aspect of things. So this talk is going to focus more on a third aspect of this project about like NIP Noetherian rings. So I wanted to first give some background and maybe justification for why I would want to look at this problem of trying to classify NIP Noetherian rings, because it's kind of maybe a weird problem to look at. Firstly, let me just give a quick definition of NIP and then a more intuitive one on the next slide. Maybe everybody here knows the definition, but since it's so important to my talk, I may as well give a definition. So one way to define NIP quickly using indiscernible sequences is that a theory has the independence property if you've got some definable set and some indiscernible sequence that oscillates going in and out of the set. Like if this is the set D, it's definable, and you have this indiscernible sequence, the first point is maybe inside or outside, and the next one is inside, then outside, then inside, and so on. And it's crossing the edge of the set infinitely many times. Of course, by indiscernibility, the set shouldn't be zero definable, or else that wouldn't be possible. So that's like a quick way to define it using indiscernible sequences. Maybe a more, okay, and so that's what it means for a theory to have the independence property. The NIP means that it doesn't have that configuration. A more conceptual way to think about it, which I believe is where the term independence comes from, is that sort of a theory has the independence property if you can draw kind of arbitrarily big Venn diagrams. So more precisely, T has the independence property if in some model you can find an infinite sequence of sets of bounded complexity, and these sets are independent in the sense that they freely generate a Boolean algebra. Like the Boolean algebra that they generate is free. There's no sort of Boolean relations between these sets. Concretely, like 3 sets would be independent if, oh, this is a laser pointer. Each of the like 8 regions in this diagram is non-empty. That's what it would mean for them to be independent. So you can think of independence in that way. And the reason why NIP is significant is that, first of all, it generalizes stable theories, which were like a central thing within model theory historically. It includes algebraically closed and separately closed fields. It generalizes O-minimal theories, like real closed fields. And it also includes many theories of Henselian valued fields, like ACVF, RCVF, p-adically closed fields, Laurent series over C, Laurent series over R, and many other theories. I guess, yeah, Delon showed that basically like an equicharacteristic 0, a theory of valued fields is NIP if and only if the residue field and the value group both are. Though it turns out the value group is always NIP, so that you just have to look at the residue field. And there's some more subtle characterization of things which Henselian valued fields are NIP in positive residue characteristic cases due to other people. Another thing that's related to NIP that's going to come up in my talk, so I'm just going to briefly introduce it, is DP rank. I think that might be short for dependence rank. I was never really sure about this. So again, we can give a quick definition using indiscernible sequences and maybe a more conceptual definition in terms of some configuration of sets. So the quick definition is that the DP rank of A over B, where A is some element or finite tuple and B is a set of parameters in a monster model, it's just the maximum number of mutually B indiscernible sequences that all failed to be indiscernible over B and A. Somehow it's measuring, when you go from B to A and B, how much mutual indiscernibility can you break at a time? So I don't know, a collection of sequences is mutually indiscernible over some parameters if each sequence is indiscernible over all the other sequences. So like that's some way to quickly define it. That's a bit abstract and maybe mysterious, though it turns out to be useful when you want to actually prove things about DP rank. Oh, and then if you have a type definable set or a definable set over some parameters, you get the rank of that set from the rank of, so this first definition is the rank of complete types, and then this is the rank of a definable set or a type definable set. You do the usual kind of thing like you would do for Morley rank or Laskar rank, where the rank of a set X is the maximum of the rank of the complete types that live in it. This definition looks like it depends on the set of parameters B, but it turns out not to. There's an asterisk next to maximum because I really want to take a supremum. There might not be a maximum value. So it turns out that DP rank is a sort of a good notion of dimension, or you can think of it as a notion of dimension for definable sets and types, the way that Morley rank or Laskar rank is. It has a lot of the usual properties, like if you have a definable injection or a surjection from X to Y, then you get some inequality on the ranks. If you have a product of two definable sets, the DP rank is additive in that way. More generally, it's subadditive if you have a certain, it doesn't have all of the additivity properties that you would expect. In some ways, it's sort of subadditive instead of additive. Like if you have a short exact sequence of groups, normally you might expect that the rank of B should be sort of equal to the sum of these two ranks, but instead you just get a sort of weaker condition that it's less than or equal. Though if the sequence splits, then you can identify B with A times C by a definable bijection, and so then you get equality in that case. But regardless of the fact that it's not quite additive, it still behaves like a good notion of dimension. And the reason I'm bringing, let me come back to that. The reason I'm bringing this up is because, so DP rank is connected to NIP the same way that it sort of governs NIP, the way that something like Morley rank governs the notion of being totally transcendental, or Laskar rank governs being super stable. Like a theory is NIP if and only if all the types have DP rank that's DP rank less than infinity. It takes values in the cardinals, so the less than infinity doesn't mean like finite. It just means that it takes sort of a well-defined cardinal value. Similar to how Morley rank takes values in ordinals, and like a theory is totally transcendental if the Morley rank is less than infinity, which doesn't mean the Morley rank is finite. It means that it's an ordinal. So here it means that the DP rank is a cardinal, basically. Oh, well, yeah, let me back up to this slide. So you can also define DP rank in terms of a certain configuration of sets occurring. So for simplicity, this is just going to talk about DP rank greater than or equal to 2. It means that you have some sequence of sets, x0, x1, x2, and so on, and another sequence of sets, y0, y1, y2. They should have bounded complexity, and you sort of should get this configuration more or less. You should get these points aij such that aij is in xi, but none of the other sets, in none of the other x sets. And ij is in yj, but none of the other sets. This picture might be a little misleading because there could be some overlaps between the x0 and x1 or whatever. It's not important that they be disjoint. I mean, it's not required that they're disjoint the way that I've drawn it in the picture. But just the main thing is the way that these witnesses aij are related to the sets needs to look like the picture. And so anyway, if you have this kind of configuration occurring inside of some definable set, then that's exactly what it means for the definable set to have rank at least 2. So the idea is this is measuring some kind of the dimension of the set. Like this looks like a two-dimensional picture. You can make analogous pictures in higher dimensions. Like you can do a three-dimensional version of this, and that'll correspond to DP rank 3, and so on. So this is basically the definition of DP rank using ICT patterns, but just described in terms of definable sets. Yeah, so that's sort of a different way to think about it in terms of something maybe a little bit more concrete, though this definition is actually kind of harder to work with when you're trying to prove things. So as I mentioned, this is sort of a natural notion of rank for NIP theories because first it has this good properties of being a dimension. I mean, it acts like it's the dimension of sets. In cases like O-minimal theories, it actually is the standard O-minimal dimension. And it's related to NIP because it's of this condition, this fact that a theory is NIP if and only if everything has well-defined DP rank. And so then there's this related notion of DP minimal, where a theory is DP minimal if it has DP rank 1. It's like how it's almost true that a theory is strongly minimal if it has morally rank 1. I mean, that's not exactly true, but it's nearly true. So maybe it's a similar kind of idea. So maybe concretely, that means that this configuration here doesn't occur. And this class of DP minimal theories turns out to actually include a lot of classes that we care about. It includes algebraically closed fields and algebraically closed valued fields, periodically closed fields, O-minimal theories like RCF. All of those are DP minimal theories. Also, if you take a lot of these theories, if you expand them with the analytic functions or restricted analytic functions, like for RCF, if you add restricted analytic functions, it's still O-minimal. And there's versions of O-minimality for these other theories, like C-minimality for ACVF and P-minimality for PCF. And all these other things like C-minimal and P-minimal, they also imply DP minimal. So anyway, it's some natural class of theories that's pretty big. It includes strongly minimal theories, O-minimal theories, and yeah, maybe it's like some analog of strongly minimal, but for NIP instead of for totally transcendental. You can also look more generally at what are sometimes called DP finite theories, where the DP ranks are finite. There's some fine print about, if you know a lot about DP rank, there's some possibility that the DP rank is less than LF0, but bigger than any finite number. So I don't want to say that like the DP rank is less than LF0, but basically I just mean that the DP rank is an actual finite number. Anyway, that's what I mean by DP finite. Okay, so that was all a bunch of abstract background about NIP, just in case some people haven't seen it before. So in this talk, whenever I say ring, I'm going to mean a commutative unital ring. I think there's lots of interesting questions about like non-commutative rings. I mean, things like the quaternions are NIP, but I'm only looking at commutative ones, commutative rings. So you could ask a natural question like which rings are NIP, and that's a very hard question. So in this talk, I'm going to look at this maybe baby case of which Noetherian rings are NIP, which is still very hard and not something we're going to solve anytime soon. But at least somehow this case is easier. And we can maybe learn things from this easier case that would point the way towards doing more general cases. So here's an example where this baby case of looking at Noetherian rings is easier. So I have a preprint where I prove the following theorem. I don't know if it's stated right, but basically we can classify DP minimal, or we can classify the Noetherian integral domains that are DP minimal. So there's DP minimal fields which have a known classification. There's basically things like the Laurent or formal power series over a DP minimal field K of characteristic 0. Or you could take like the QP or some other local field, like another finite extension of QP, and look at the either look at the ring of integers in that, or I mean whatever you call that one, you know, like the usual evaluation ring, the thing that's like ZP or whatever, but in your bigger field. Either look at that ring or look at a finite index subring, which could be something like, so if you took something like, you take the 3 adic numbers and maybe add square root of -1, then I forget what this ring is called, but anyway, this like ring of integers or whatever, it's going to be the 3 adic integers adjoin I think. But you could take a smaller ring inside this that's going to be kind of bi-interpretable with this. It's still going to be DP minimal, and that would be the ring where you adjoin 3 times I. So that's an example of what I mean by like a finite index subring of one of these rings. So that ring it's not a valuation ring, unlike the other things there. This isn't the valuation ring, but it's really close to one. It has like finite index in this valuation ring. So you get a few examples like that, and that turns out to be the classification. I mean, you don't want to just say classify them up to elementary equivalence, because Noetherianity is not preserved in under elementary equivalence, which maybe means it's a bit weird for me to be like, it's a bit of a weird question to like try to classify Noetherian NIP rings, since it's not an elementary class at all. But I don't know. I think of it as like how Noetherian rings are not an elementary class, but neither is the class that just has like the class of we care about the real numbers like by themselves, and that's not an elementary class. But by doing model theory, we can learn useful things about it. And so I don't know. In the same way, if we find some NIP Noetherian rings, then we have some useful model theoretic tools to apply to them, even though they're going to have elementary extensions that are not Noetherian. So maybe that's the mindset of why why you could look at this thing. Yeah, so this was supposed to be an example of how maybe looking at Noetherian rings is easier than the general case. So to compare, in contrast to this thing, the more general problem of classifying DP minimal integral domains is not yet known, I think. I mean, so there's a paper by Christian and Yatir, and they prove lots of things, but it's not yet to the point of a classification of DP minimal integral domains. I also thought about this a lot, and I couldn't find a classification either. I think now there might be kind of a plan that will work together on this problem. But yeah, so my point is just that by looking at the special case of Noetherian rings, it can be easier, and it might point the way towards how to consider the more general case. Oh yeah, so I mentioned that these problems are still really hard and not going to get solved anytime soon. So part of the problem is that this problem of classifying NIP Noetherian rings includes the problem of classifying NIP fields, which includes the problem of classifying stable fields, which is a long-standing open problem. So none of these things are going to get answered anytime soon. But we can still prove some interesting results about things. But anyways, that suggests that maybe there's sort of two routes we should take. So one option is to focus on cases that have low DP rank. Like I gave an example of, here's a classification of the Noetherian rings with DP rank 1. Another option is to just assume these kind of standard conjectures on NIP fields. And maybe assuming those conjectures, we could figure out what the classification of NIP Noetherian rings should be. So maybe here's an example of a result in that direction. So Sylvia and Hansi have a paper where they basically say what the exact classification of NIP fields should be, assuming certain conjectures. Basically assuming the Shalot conjecture that says something like any NIP field is going to have a Henselian valuation on it, unless it's finite or the real numbers or a few other cases. So almost all NIP fields are Henselian fields, is this conjecture, and assuming that, they can actually get, that seems like a very weak statement. Well, it feels like it gets you halfway towards a classification, because if you know every field comes from a Henselian valued field, then sort of Axe-Koch and Ershov tells you need to classify the value group, and we can understand what those are. And then you need to classify the residue field. But the residue field is just another NIP field, and you haven't gotten anywhere. But nevertheless, using the sort of canonical Henselian valuation stuff I think by Jochen and Franzi, there's a way out of this loop, and then you can get an actual classification of fields from this conjecture that you always have Henselian valuations around. So if you assume that, or if you assume this weaker conjecture called the Henselianity conjecture, it just says any NIP valued field is Henselian, or Henselian, whatever. If you assume either of these two things, you can prove the following, that, for example, NIP Noetherian rings are, or at least integral domains that are Noetherian, are going to be Henselian local rings. And more generally, I think NIP rings are going to be a finite product of Henselian local rings. So somehow, assuming a statement about the fields, you could learn something about the rings. And again, I don't know how to do that implication for a general NIP ring. So somehow, again, we see the Noetherian case is easier. So the next section is just sort of a summary of some basic facts that you can prove about NIP Noetherian rings. So here's a fact that, so this was I saw this in the paper by Christian and Yatir, and they attributed it to Pierre, but it might be some folklore thing, because I think that this is on one of the posters outside as well. So this is fact that if you have an NIP ring, you can't have an infinitely many incomparable prime ideals. Like, so if you've seen NIP before, a simple example of of a ring without NIP is the integers. And you get, the simplest way to get the independence property is somehow use the divisibility and use the fact you have infinitely many primes. And there's some not very complicated argument using that shows more generally, if a ring has like a anti-chain of prime ideals that's infinite, you can get the independence property. So conversely, if you are NIP, then there's a bound on the size of anti-chains of prime ideals, which actually means that due to some facts and like some combinatoric fact, like Dilworth's theorem or something, that really means that your poset of prime ideals in the ring is going to be a finite union of chains. So in the NIP ring, we know that the poset of prime ideals really is just a union of finitely many chains. And so from that, you can see some things like if you have a Noetherian ring that is NIP, well, it's going to be semi-local. I think this is the right term for a ring that has finitely many maximal ideals. Like a ring is local if it has one maximal ideal. I think semi-local is what you call it if you got finitely many. So yeah, well, of course, it's from the previous thing. If you had infinitely many maximal ideals, you'd have an infinite anti-chain. So that can't happen. Instead, you have finitely many. But actually, so for Noetherian rings, like you can't have an infinite chain of ideals. Noetherianity tells you you cannot have an infinite ascending chain of prime ideals. Sorry. In a Noetherian ring, you cannot have an infinite chain of prime ideals. This is like it's a non-trivial theorem in commutative algebra, but it's something you learn if you ever take commutative algebra up to a certain level. Like Noetherianity already tells you cannot have an ascending chain of prime ideals, but the sort of dimension theory on local rings and local Noetherian rings tells you that every prime ideal has a well-defined height, and the height is finite, and it goes down when you have it in a chain. And so there's really not possible to have a descending chain of prime ideals either. So I just mentioned that in any NIP ring, if you look at the set of prime ideals as a poset, it's a finite union of chains. Each of the chains is finite in this case, so you only have finitely many prime ideals total. Okay, that's like something it's not going to be preserved in elementary extensions at all, of course. And then another interesting thing that comes up from the local or the dimension theory and local rings or this Kroll ideal theorem or whatever, all that business, is that if you have a Noetherian ring with only finitely many prime ideals, it has to have Kroll dimension 1. So that just means there's no chains of prime ideals that have length greater than, you can't have 3 consecutive prime ideals like this. There's a reason for this. Well, there's something to do with, there's a certain reason why if you have 2 prime ideals with another prime ideal in between them, there's always going to be infinitely many. It's something like, I can't remember off the top of my head, but it's some simple reason involving like something like the Kroll principal ideal theorem or something. I think if you take an element pretend this is the ideal 0, which you can reduce to. You take element that doesn't belong to any of these prime ideals, but it does belong to this one, and then you look at the minimal ideal over it, and Kroll principal ideal theorem says it has to have height 1, but we chose it to not be any of these ideals and instead be that one. So something like that works, and you see that the ring has to have Kroll dimension 1. So basically, at most you have finitely many maximal prime ideals and finitely many minimal prime ideals. If you're an integral domain, there's only one prime ideal, and you get this kind of picture. You have the minimal prime ideal 0, and then you have finitely many maximal ideals. So yeah, maybe this is sort of self-defeating, because now it seems like this is kind of giving away the fact that basically almost no Noetherian ring that we care about is actually going to be NIP. I mean, almost all of the ones that come up in practice are not one-dimensional local rings or whatever. Nevertheless, I think there are still some interesting problems. Like, it's not trivial to try to classify NIP Noetherian rings. And it seems that there are some really weird examples, which is useful to know. Like, it's useful to know that there are strange examples of NIP theories. So anyway, okay, so that's the first thing that you can see about the about NIP Noetherian rings. This fact that the spectrum, the set of prime ideals, is really simple. It just looks like this. In fact, it should be even simpler, as I'll talk about later. But then there's this weird thing that comes up. So here's a definition. This might have some other better name. I'm calling it the breadth of a ring. I was originally calling it weight, and then I learned that in lattice theory, this is related to something in lattice theory called breadth. So anyway, I'm calling it breadth now. So the breadth, I'm defining the breadth of a ring R is less than or equal to k if this following thing is true. Basically, whenever you have k plus 1 elements, the ideal that they generate is generated, you can throw away one of the generators. Like any given A0, A1 up through AK, you can omit one of the, this notation means the ideal generated by A0 through AK. So I guess it's saying something like, if you have a minimal set of generators for an ideal, it has to have size at most k. If you think about what this means in the case of breadth 1, it actually just says that R is a valuation ring. Like, it's saying that for any A and B, either A is already generated by B, or B is generated by A. It's saying that either A divided by B is in the ring, or B divided by A is in the ring. And that's just the definition of a valuation ring. So these rings of finite breadth maybe are some kind of generalization of valuation rings or something. So this definition kind of came up in my project of classifying fields of finite DP rank, because it turns out that those fields have some sort of canonical topology on them that is sort of always induced by one of these rings. If the ring has breadth 1, it's induced by a valuation ring, and then it's a V topology. But in general, this canonical topology I was looking at is not a V topology. It's instead something more mysterious. But so anyway, this definition came up in this other project, the project of classifying finite DP rank fields. But it turns out it's relevant here, because there's this fact, it's basically due to Irvin Cohen, saying that at least for Noetherian rings, something has finite breadth, if and only if it's a semi-local ring with curl dimension at most 1. So in particular, NIP Noetherian rings are always going to have finite breadth. I think what Cohen proved is something slightly different, or it looks different. He looked at the class of rings where every ideal is generated by at most k generators, which is kind of looks complementary to this, because here we're saying that we're not saying every ideal is finitely generated. We're just saying if you are finitely generated, then you can throw away generators until you have only k left. And also, we're not getting to rearrange. In the definition of breadth, we don't get to choose different generators. And the thing that Cohen is defining, you could maybe choose a different set of generators than the one you started with. But assuming Noetherianity and using some argument with Nakayama's lemma, I think you can show that you can turn his result into this fact I wrote here. Yeah, so then this is why I brought up these rings of finite breadth, because it includes NIP Noetherian rings. It doesn't include arbitrary NIP rings or rings of finite DP rank. Like, there's an example from, let me see. I probably won't write this out correctly, but if you take like a algebraically closed valued field of characteristic P, and you take the maximal ideal, and then you add like FP to it, then that's going to be a DP minimal ring that's not, doesn't have finite breadth, it turns out. Yes?
So what less than infinity means like breadth equal to breadth less than k?
Oh, sorry, yeah, it means less than, yeah. I mean, Well, yeah, exactly. That's a good question. Sorry. I mean that there is a k finite such that the breadth is less than k. Yeah. So one thing to note is that this condition of having breadth less than k is actually elementary, unlike Noetherianity. And actually, maybe a lot of the results I'm giving in this talk are, some of them generalize to these rings of finite breadth, which isn't actually an elementary class. That does come up naturally when you study DP finite fields and study the topologies on them. So maybe this was an excuse to actually talk about those things. But yeah, so like if you take an Noetherian ring that's NIP and you go to an elementary extension, it'll still have a few nice properties. Like it'll have finite breadth, and that'll imply some interesting things. Like, so if you have finite breadth, so I meant to say if you have breadth less than k, then every finitely generated ideal is generated by k generators or fewer, because that's the definition. You throw away generators until you have only k left. But that's interesting because then it implies every ideal is externally definable. So it means the class of finitely generated ideals is uniformly definable, is bounded complexity, and any ideal is a directed limit of FG ideals. And if you have a directed limit of some sets that are a directed union of some sets that have bounded complexity, that'll always be externally definable. And externally, I don't mention it here, but externally definable, there's a theorem of Shalad saying that if you can add externally definable sets to your structure and you'll still be NIP. This is a key tool for working with NIP fields and other NIP structures and stuff. So you can almost pretend that all the ideals are definable. Even better, you can show that, or related to this, you can show that all the overrings are externally definable. So an overring if you have a domain, an overring is the ring between the domain R and its fraction field. So something like the integral closure or localizations, these kind of things. So you can show these are also externally definable if the ring had finite breadth. And the trick here is that, so I gave the definition earlier of the breadth of a ring. You can also talk about the breadth of a module. It has some interesting properties. It's sort of subadditive in exactly the same way that DP rank is. Like if you have a short exact sequence of modules, you get the same equality that I wrote down, which is somehow related to why it comes up in this context. Anyway, you can talk about the breadth of modules. It turns out the field of fractions has the same breadth as the ring itself. So if you started with a ring that had breadth 5, then the field of fractions also has breadth 5. And then you can run the same argument, and you see that all the submodules of K are also externally definable. So in particular, any overring is externally definable. So you can assume that things like you can't assume the integral closure is definable, but you can, it's like if you add the integral closure as a predicate to your structure, it'll still be NIP, and you get some good consequences from that.
Now, externally definable where? In the field?
Yeah, sorry, in the field. I mean, sure, it's like externally interpretable, I guess, because the field isn't really definable, it's interpretable, but yeah.
In the ring. In the field, with the ring named with the predicate.
Yeah. Well, so yeah, that structure is bi-interpretable with the original structure, of course. So yeah, these overrings are all going to be NIP as well. That's the point. So like I mentioned, any localization is going to be externally definable. Any evaluation ring that contains R is going to be externally definable. Also, there's I guess there's a theorem in commutative algebra called Kroll-Akizuki theorem that says that if you take a one-dimensional Noetherian ring like we're looking at, and you go to one of these overrings, it's still one-dimensional Noetherian. This is maybe important in commutative algebra because it tells you if you take integral closures, you still are Noetherian, which can fail in general. And so that is going to get combined with something. Sorry for this confusing presentation. There's a fact that, for NIP discrete valuation rings, they have to be either equicharacteristic 0 or mixed characteristic. So I just mean the residue field, they can't have positive characteristic. They can't be equicharacteristic P. It comes from this fact that this Kaplan-Scanlon-Wagner theorem saying that if you have a positive characteristic NIP field, it's closed under the Artin-Schreier map is surjective. This turns out to be true, and it implies you can use it to see that an evaluation ring in a positive characteristic valued field, I mean, the value group is always divisible. So if you had a discrete valuation ring, that couldn't happen. And so, the only valuation rings that are Noetherian are the DVRs, the discrete valuation rings. So using this and combining all these things, you can show that if you have an NIP Noetherian domain that's not a field, then it has to sort of have characteristic 0. The diffraction field must have characteristic 0. I mean, I think the rough idea is just, you just take this ring R and just take any valuation ring containing it, and that'll be Noetherian. It'll be NIP because it's externally definable. And then just apply that theorem to any valuation ring, and you see that the ring has to be the field that this all lives in has to have characteristic 0. Yeah, I mean, I guess we need the fact that every ring is contained in a valuation ring, and that comes from this fact that sort of any local ring is dominated by a valuation ring. You can also, by being more careful with this argument, you can show, I'm going to keep writing on that. You can also show that there should only be one maximal ideal. So I drew this picture here of what the spectrum of prime ideals looks like, but actually, assuming all the conjectures are true, there's only one prime ideal. It should just be a local ring. Sorry, one maximal ideal. So the thing I wrote up there is a conjecture that's a form of the Henselianity conjecture. Earlier I mentioned the Henselianity conjecture, which says any NIP valued field is Henselian. It's equivalent, it turns out, to this statement up here. It says if you have two valuation rings on K, and you look at the structure where you name them with predicates, that thing, if that's NIP, then the two valuation rings have to be comparable. So basically, in an NIP setting, any two definable valuation rings on a field should be comparable. That's actually equivalent to the Henselianity conjecture. I think some people in the room proved it. I think I won't say how the proof is quite nice, but I think it's not my proof, and I'll just skip that. So that's the conjecture. It's true, and so for finite DP rank things, we know the classification of fields. We know all the conjectures, or at least if my preprints are right. Hopefully they don't have some big error. So we know that DP finite valued fields are Henselian. We know what all the DP finite fields are, and so on. So in particular, this theorem is true. This conjecture is true for if you're in a finite DP rank case. So what you can prove is this thing, that if you have a NIP Noetherian domain, if the Henselianity conjecture holds, like that in that form up there, or if everything is finite DP rank, then you can show that R is actually a local ring. The idea is pretty simple. So there's this basic theorem in valuation theory, I think it's due to Chevalier, that says if you have a prime ideal on a domain R, then you can find a valuation such that basically there's going to be a valuation ring that dominates the localization, but I think what that means concretely is that the valuation is non-negative on R, and it's I don't know, positive on the prime ideal, but then it's 0 off of the prime ideal, something like that. So something like that is true. Some basic fact, I think, due to Chevalier, maybe. So what you do then is you apply that fact you just take two different maximal ideals. You apply that fact to get some valuation rings, and these valuation rings are automatically externally definable because of this finite breadth nonsense. And so, and it turns out they're incomparable if you start with two incomparable maximal ideals. So you get two incomparable valuation rings. That's not allowed by the conjecture. Sorry. And so Yeah, so you very quickly can show that these things, assuming all the conjecture about Henselianity, you can very quickly get that NIP Noetherian ring should actually be local. So really, this picture should just have one maximal ideal. You should just have maybe one maximal ideal, and then you have the zero ideal. And that's it. Those are the only prime ideals in your ring. I don't know why I mentioned that the spectrum. I mean, sure, it's linearly ordered. It only has two things. I think that I mentioned this because I mentioned some of these results are true for elementary extensions. For an elementary extension, you can have way more prime ideals, like an elementary extension of ZP. ZP is a good example of a DP minimal Noetherian ring. Elementary extension have way more prime ideals, of course, but they're still going to be linearly ordered. So that's a statement that's true if you are if you have finite breadth, and if these conjectures are true in your NIP. So using that, though, you can actually show that no, not really using that, but just you can also show the integral closure is a Henselian evaluation ring. So integral closure is the intersection of all the evaluation rings that contain R. And assuming this conjecture, they should all be comparable because all those valuation rings are going to be externally definable. So you end up getting an intersection of a chain of valuation rings. It's still a valuation ring. And also the Henselian conjecture tells you it's Henselian. So if we have these additional conjectures, or if we're in a case where we know the conjectures are true, we can say like a bit more than just this picture of like this. We can say there's only two prime ideals, and this thing is a Henselian local ring. The integral closure is a Henselian discrete valuation ring. And also, it turns out you can show the ring R is a Henselian local ring. Yeah, I think I maybe presented this a bit out of order, but yeah, it's true that, so here's another thing, that under those assumptions that either these conjectures about Henselianity are true, or that we're in a finite DP rank case, any NIP Noetherian ring is going to be a finite product of Henselian local rings, and if it's a domain, then it has to be a single Henselian local ring. Yeah. So I don't know if this is a sensible conjecture, but I've made it in a couple talks so far, and nobody's been like, well, here's a counterexample. So I want to make this conjecture that maybe any NIP ring has this property. Any NIP ring is a product of Henselian local rings. It turns out this is equivalent to several other conditions, like every NIP integral domain is a local ring, or every NIP integral domain is a Henselian local ring, and there's some other forms of it. Yeah, it would be nice if the NIP field conjectures imply this, but I don't know how to prove that yet. One of the motivations for this, or some justification for this generalization of the Henselianity conjecture is that it's true in positive characteristic. It's also true in finite DP rank. So maybe it's not completely outlandish. But I guess the point of this slide, though, is that it's true for Noetherian rings. It is true, assuming the usual other people's conjectures that are maybe more like justified or whatever. You don't need to go to some more general conjecture. You just get it from the usual Henselianity conjecture. But yeah, do you have a question?
So in the case of finite DP rank, you can drop it.
Yeah. Oh, sure. Oh no, this isn't. This is supposed to be for any. This is dropping Noetherianity. Yeah, for finite DP rank rings are products of Henselian local rings, I think. Yeah, what's your question?
What if your ring R is real numbers?
Oh yeah, so I mean, it's a field. Or if you count a field as a local ring, then yeah, I'm kind of counting a field as a local ring because it has a one maximal ideal.
What about the dual domain?
They're not a domain. I mean, they're a Henselian local ring. The dual numbers, I think, are Henselian local ring. Yeah, okay, sure. Every Artinian ring is Henselian. Good. Okay, so, sorry, was there some other questions? Sorry, wait. Oh, yeah, sorry. I'm kind of sorry that I'm switching randomly between domains and rings. I mean, the theorems are nicer for domains, but there's also things that are true about rings that seem much more general, and so it's nice to state both sometimes. So I guess now I'm going to move on to a lot of what I've been talking about so far is in not assuming DP finite necessarily, and then of course we can't say much, and we only have to assume a bunch of conjectures. So now I want to look at the more like cases of really low DP rank, like DP rank 1 or DP rank 2. So it turns out in this case there's already some more things we can say. This is not a theorem. This is not some result from the talk. This is some fact that was established 10 years ago or something. I don't quite remember who actually proved this. Anyway, it's some classification. It's not important to read that. It's just the point is there's some classification of which valued fields are DP minimal. Oh wait, that says DP finite, so I guess I proved that. Sorry, I was thinking of some earlier theorem about DP, so yeah, some other people classified DP minimal valued fields, and then I guess I extended it to DP finite fields. So there's some way to characterize when is a valued field DP finite. It's like the residue field has to be DP finite, the value group has to be DP finite, it has to be Henselian and defectless, and then there's some extra condition on some random conditions, but they are what they are. Anyways, that characterizes DP finite valued fields in terms of the residue field, and then you can also classify what the DP finite fields are. And I'm not going to say the classification, but the idea is that somehow they all come from valued fields, and this machinery that gives you a new valued field from the residue field that generates it sort of generates all of the DP finite fields. Like all the DP finite fields come from valued fields, from DP finite valued fields, where the residue field is the real numbers are algebraically closed or finite or something. So you start with some known examples, and you expand outwards using this Axe-Cochin-Ershov-like principle. That'll give you all of the examples. Yeah. Anyway, then you look at this and you see which of these valued fields are like discrete valuation rings, like which of them are Noetherian, and it turns out it's just these ones. So the DVRs, like the discrete valuation rings that are DP finite, are just the following things, and maybe they're elementary substructures. So you have like the formal power series over a DP finite field, and you have the like ring of integers in QP or some finite extension in a p-adically closed field. So that's the classification of discrete value of the valuation rings. And now if I have some random Noetherian ring, I can look at its integral closure, which is also going to be an NIP Noetherian ring that's a valuation ring. And you can get some kind of trichotomy you just get three cases. You get like, okay, you could start with a field, or you could have something that sort of has residue characteristic 0, or you could have finite residue characteristic. Sorry, a finite residue field. Like, if you have a Noetherian domain that's DP finite, either it's a field, or it's like some local ring that's not a field where the residue characteristic is 0, and it's got an infinite residue field, or it's got a finite residue field, like ZP, that kind of thing. And the integral closure is going to have the same exact properties, and then from the previous slide, that tells you what the integral closure looks like exactly, and you can work backwards from that to figure out what the ring itself looks like. So the idea is maybe, yeah, if you try to classify these things, you start with, take the ring R that you're trying to understand, go to its integral closure, understand the possibilities there, and then work back from that to figure out what R is. So whenever you have a semi-local domain, you get like a field topology from it. If you have, there's sort of, like if R is a semi-local domain and it's got a fraction field K, and R is not a ring, sorry, not a field, then there's always like a field, it induces a field topology on its field of fractions. You can describe it in a couple ways. One of them is that the sort of rescaled versions of R, like multiplied by a non-zero constant, those are going to be a neighborhood basis of 0. You could also look at the non-zero ideals. They will also be a neighborhood basis of 0. Anyway, this thing exists. It's sort of if you start with a valuation ring, it's the usual valuation topology. So somehow, this is some kind of generalization of that. This comes up a lot in this paper by Prestel and Ziegler about model theoretic methods and topological fields or whatever. So that was a little aside. Now the point is there's sort of what you can do if you're trying to understand this ring R that's a Noetherian finite DP rank ring. You look at the topology, it's a local ring. Or it's definitely semi-local, and if the Henselianity stuff is all true, then it's local. And so it induces a topology on its field of fractions, and if we're lucky, it's the same topology as the integral closure. The integral closure is always a valuation ring, so it induces a V topology, and in the lucky case, R induces a V topology. So in that case, sort of R and the integral closure O are really close to each other. What you can show, well, this is like a theorem in question marks because I haven't proved it, and also it's not a very clear statement. So there's basically, yeah, there's sort of two things that could happen here. One of them is that you're something like this example here, where you have a finite index subring of one of these ring of integers in a p-adically closed field, something like that. That's kind of one possibility. The other possibility is something like this example here, where you've got something that's kind of like a finite dimensional index in the other kind of ring. So like O is the integral closure of R is either going to be something like Z3 or whatever, or it could be something like power series. So in the power series case, you can get some other weird examples like this kind of ring. So that's what happens in the lucky case where you have a V topology. And it turns out in the DP minimal case, that always happens. Like on a DP minimal field, you can never actually have any, there's only one definable topology always. It's always a V topology. It's always T Henselian and very nice. And so if you take your ring R and you look at the structure KR, like the fraction field with a predicate for R, you apply that fact and you get that the topology that R induces is a V topology, and you're in this lucky case. There's something subtle going on here, which is that the fraction field, when you go from R to the fraction field, you would think the DP rank goes up. Like to give an element to the fraction field, you have to give to the numerator, like it's a fraction, A over B. You're specifying two different values. So you'd think like that could be twice the dimension of the ring you started with. But there's some weird trick that shows that actually the DP rank stays the same. And somehow, like if you have some witness to the DP rank being a certain, at least K, you can take all these witnesses and like multiply them by something and move them into R. Or take some kind of common denominator and multiply them by the common denominator and turn all the witnesses in the definition of DP rank to be elements of R. And this is weird trick that works. So actually, when you go to this structure KR plus times, it's still DP minimal, and this theorem I mentioned up here applies. So anyway, you get a V topology in this case. Like this ring R is inducing a V topology. And you get this classification I mentioned earlier. Which I mentioned it earlier and discussed it a bunch, so let me just move on. I don't know why I put this here, but I mean, I think I mixed up, I mean, this should have gone earlier. Like, I mentioned it earlier that like, that Christian and Yatir have this like paper on DP minimal integral domains. Oh, and I think part of this is like I mentioned that like we don't know how to classify DP minimal integral domains, but there is something very strong you can say, which is that if they have infinite residue field, they have to be valuation rings. And somehow the remaining difficulty is classifying finite residue field case. Yeah. And so I think I put it here because if you know that, then a lot of what I'm doing up here is kind of very easy. Or like you can use this to get a lot of the thing up there. So am I supposed to stop now or I can keep talking? Okay, sure. So I want to say a little bit about what happens in DP rank 2, because I think it's really interesting. So I don't know if this actually works, but I think that there are weird examples starting in DP rank 2. So you can take the theory of p-adically closed field, add a generic derivation. And take like the model companion. This theory exists. I think it's NIP. I think maybe these people proved that it exists and it's NIP. I could be wrong. And if you take this, oh, okay. Did you guys prove it existed? Okay. So I think if you look at the axioms, you can see that you can take the standard QP and expand it, choose some derivation on it that's sufficiently random and get like a model of this theory. Okay. And now if you look at this ring, the elements that have valuation at least 0, and the derivation also has valuation at least 0, you can check that that is a Noetherian ring. It's interpretable in this structure that's NIP, so it's also NIP. You can also check it has like the fraction field in this case is QP. The integral closure is ZP. It does not induce a V topology. So the thing I don't know is, I don't know if this example has rank 2. But backing up, the ways that this example is really weird is you don't get a V topology. It's also not, so there's a bunch of random stuff in commutative algebra, like N1 and Japanese rings and excellent and all these. They all start with this definition of, like, the first nice property that rings need to be excellent is that the integral closure is finite over them. And that's not true here. So ZP is not finite over R, and that's part of why the topology from R is not the p-adic topology. But I don't know if this example has DP rank 2. But I think it might, because if you do everything with algebraically closed valued fields instead of p-adically closed fields, you do get something of rank 2. But you don't get something Noetherian, which is what I was looking at in this talk, so I don't know. Also, like, the proof I have of this is really terrible. I used some facts from some book on almost mathematics. I don't think I'm actually using the almost mathematics, but it all just left me feeling that it was some very scary subject. And also, like, log derivative, or like log math, I don't know, like this log algebraic geometry was there for some reason. So like, let me give a sketch of why this theory is really weird and terrible. Or not, okay, so if you start out with that theory, the thing that's definitely NIP, like it's not strongly dependent. It has like really high DP rank, basically, if you include the valuation and the derivative. It's sort of because I think it's because if you take an element A and you look at the sequence of derivatives, there's no topological relation between them. They can be moved arbitrarily through space, and you get an ICT pattern of however high you want. I mean, up to the maximum. Okay, so we can't work in that theory, that structure, because it's not finite DP rank. So instead, you work in this structure, which is finite DP rank. So you take the derivative, and you sort of compose it with the map sending k to k mod O for some weird reason. That's enough, though, to give you this ring. But when you try to like prove things about that theory, like quantifier elimination, it's kind of lame, or it's super confusing what happens, because like this theory, I think it doesn't have quantifier elimination, because there's some kind of issue where this theory knows a bit more information than it claims to know. Like, you can tell this truncated derivative is supposed to forget a bunch of information, but if you take the derivative of x squared, it's 2 times x times the derivative of x. If you think about how much precision there is, somehow the right-hand side has more precision than the left-hand side. And so what you could do is take an element x, take its square root, use this formula, and get more information about the derivative than you're supposed to know. And this messes up quantifier elimination. So instead, you do something even weirder. You take the log derivative, multiply it by that thing, and then this theory, for some reason, has quantifier elimination and has DP rank 2. It's also enough to find that ring up there. This is only for the algebraically closed valued field case. I don't know what happens in p-adically closed fields. It seems like a mess. I don't want to think about the positive residue field characteristic case. So yeah, I think that maybe so here are some really vague conjectures. I think there are going to be examples of Noetherian rings of rank 2 coming from this. They're going to be really weird because they're not going to be excellent. They're not going to be N1, whatever that is. I also think maybe these are going to be the only examples. Like I made it look terrible, but I think that the situation isn't hopeless, because I think these might be the only actual examples. And part of why I think that is, I think that there's a way to do something like what I did in the DP rank 1 case. In the rank 1 case, I knew this fact that this is canonical topology, it's always a V topology. And it turns out in the rank 2 case, I can say something, this canonical topology is not always a V topology, but when it isn't, I can say that this should be characteristic 0, but it's okay, because I'm looking at Noetherian rings, they're always characteristic 0. If you have this like field of DP rank 2, maybe it's an expansion of a field, has extra structure, then any definable topology on it is either going to be a V topology, or it's one of these things coming from a derivation and evaluation in the exact manner I was just describing. So that seems surprising, and it suggests that maybe that's the only source of these weird examples in rank 2. And who knows what's going on in higher ranks. It seems like it gets even more complicated. So yeah, there's going to be some valuation ring and some derivation, and they're actually sufficiently independent from each other, and you form this ring R in the same way that I gave earlier, and that ring induces a topology, and that's going to be the topology you're looking at.
When you say the ring, you mean definable one?
No, they're just some random, like, no, they're not. I think maybe you can make them live in some externally definable, you can make the valuation ring be externally definable, probably. The derivation, well, it's like how even in this example, this derivation, we're throwing away the derivation in order to get DP rank 2. So the derivation shouldn't be definable at all, and we need it just exists. It's just not definable at all. But the point isn't really so much that there's a derivation, it's just that this is the sort of topology you're going to get, and understanding that sort of topology would be like the method for understanding rank 2. So maybe you could say that there's some better way to present this kind of topology that would be actually more canonical. Or like the derivation is not a real thing that exists here. You can find the derivation, but really the important thing is the truncated derivation or something.
And that's definable.
I guess. Or externally definable or something. Who knows? I'm not really sure about what's going on in this case. Yeah, okay, so sorry I went maybe a little bit over time. The things I talked about in this talk were from these 3 different preprints I have. Not really, the main thing was this last one. It's just some of the stuff I talked about was from these earlier papers I had on finite fields of finite DP rank. So that's it. Are there any questions?
I just have a couple of very simple questions, if you could repeat. I think one thing you said is that the integral closure in some setting is NIP, even though it's not externally definable. Or maybe
no, like the cases that I was looking at, usually the integral closure is going to be externally definable.
Okay, so there's no result about it being NIP despite.
No, it's NIP because it's externally definable.
Yeah.
I probably said it wrong, but yeah, I meant to say it's NIP because it is externally definable. Which is not true in general, by the way. So this example of a DP minimal ring.
So can you repeat that? That was my second question, actually. Can you repeat this example?
Sorry, yeah, you take a ACVF PP and algebraically closed valued field characteristic P. Take the maximal ideal in that valuation ring and add FP. This gives you a ring that's interpretable in ACVF. And so it's like DP minimal. But I think that the integral closure here is something weird. It's not a valuation ring. It's not externally definable. I think it comes out to be something like FP alg plus the maximal ideal. It's not even a finite DP rank. So that example is very different from the ones I was looking at. And maybe in the Noetherian case or the finite breadth, I brought this up because it's not finite breadth. Like whatever, for some reason it's not, and you get this very different behavior. Yeah, so I tried to figure out go back through my notes and my preprint and figure out where it came from. I think there's so the thing is I did this long project of working on DP finite fields and kind of had a lot of dead ends, and paper number 3 in the sequence doesn't lead anywhere. But paper number 4, I didn't know that yet, so I was building off of paper 3. So everything in paper 4 is phrased in a weird way. But when you go back and understand what's it from a better point of view, I think it's you got some ring R that has breadth 2. You take the integral closure, let's call it O. It turns out to be an evaluation ring. And then, let me think. You look at O modulo R. And this is an R module in a natural way. And it turns out you can kind of extend it to become an O module by continuity or something. Like, given an element of O, if you want to multiply it by this thing, you take a very close element of R. R is going to be dense in O for if you set up things in the right way. That makes this into an O module. It turns out to be isomorphic to K modulo O if you set it up right. And then this map from O to the quotient that we're identifying somehow with K modulo O. This is the derivation, but it's like only a truncated version. It's only defined on O, it only goes to here. And then maybe that's like the more canonical object that actually exists. You can play some game to like lift it to one that is defined on all of K and like actually it goes. You start out with only having a derivation that goes from O to K modulo O. But then you can find some way to make, like this is the thing that really exists, but there's some way to turn it into one up here that doesn't really matter, but it looks nicer when you state the theorem, that there's an actual derivation on the field. Yeah, so, but the key thing is actually a derivation from O to K modulo O. And it comes from this machine of taking O modulo R and turning it, which is naturally an R module, turn it into an O module by continuity or something. And then the natural, just the quotient map from O to O modulo R, when you identify O modulo R with K modulo O, it turns into a derivation for some weird reason. But that's literally how it works, yeah.
How is the identification of O modulo R with K modulo O?
It's like, so what happens is that this thing, once you make it be an O module, it's like, I don't know, it's like a limit of modules that, like K modulo O is a limit of, is an increasing chain of some modules, cyclic modules or something. And this thing is an increasing chain of cyclic modules in the same way. So it has some very non-canonical identification of K modulo O. In fact, you can't even identify them unless you go to like a resplendent model. But if you go to like a Aleph-1 saturated model or something, then there's some way to identify that with that.
So it's definitely not likely to be definable.
Yeah. Oh, probably not externally definable either. It's just a thing. So maybe a better way to think of it is not so much that you have a derivative from O to K modulo O. It's like you have a derivative from O to some other module M. And then M has properties that make it look exactly like a K modulo O.